So these are some problems on spherical or curved mirrors, the image formation by curved mirrors. So here's the first problem. So it says a concave mirror. Concave mirror means it's a converging mirror, right? It forms a real image 25 centimeter from the mirror surface along a principal axis. If the corresponding object is at 10 centimeter distance, what is the mirror's focal length? And then sketch the ray diagram. So it's given the image distance, object distance, and this is asking you to find the focal length, and it's really straightforward problem. So first of all, it's uh, it says real image is formed at 25 centimeter distance. So di is 25 centimeter, right? Is plus because it's real image. An object is placed at 10 centimeter distance. Of course, this object is real. So what's the focal length? So then using the mirror formula, which is same as lens formula, 1 by do plus 1 by di, then you can find the focal length, right? So 1 over 25 plus 1 over 10 inverse, and that's going to give you positive 7.14 centimeter. And positive makes sense because it's converging. That simply means the focal length, positive simply means it's a converging mirror, which is concave mirror. And then it wants you to draw the ray diagram. So it's a concave mirror. So its shape is like this, right? And its focal length is, now we know the focal length is about 7, right? Let's say this is the focal length, right? And it's symmetrical if you need. So an object is placed at 10 centimeter distance, so a little further away. So right here, right? Let's say this is the object, and then what's the position of the image, right? So that's the question. So first, again, we're gonna need those two special rays, at least two special rays. One is P ray, parallel ray. That means any light ray, right, parallel to the optical principal axis will have to go through the focal point, right? That we know. And the other point in mirror, the other ray you need is M ray. M ray means a ray passing through the midpoint of the mirror, and we know how this is a mirror, so it reflects with the same angle of incidence, right? That we know. That's the trick. So they will meet at a point like this, right? And they intersect. These two reflected ray will meet. So this is P ray and this is M ray, reflected M ray, right? Because we know this reflected M ray will have must make exactly the same angle, right? Angle of incidence, and because this is the normal, and you get a real inverted image. So this is the final position of the image. Right? This is the object. So here's the next problem. So this is a problem on convex mirror, which is diverging mirror. If an object is placed 14 centimeter in front of a convex mirror of focal length 10 centimeter, right? Then it's actually describe the nature of the image formed by the mirror. So first we can first solve numerically. So its focal length is 10 centimeter, right? But make sure you have to be careful because it's a convex mirror. Convex mirror means it's a diverging mirror, right? So diverging mirror has negative focal length, right? It has a virtual focus, so yeah, you must make it negative. And object is placed, so that means the object distance is 14 centimeter and object is real. So then we're gonna find the image distance using the mirror formula, so which is 1 over f minus 1 over do, right? Inverse. So 1 over f means negative 10 minus 1 over 14, right? And negative, right? And you can do that. So 1 over 10, 1 over 14, right? So it's going to give you 5.8. So, but negative 5 point, right? 83, 5.8 centimeter. So negative simply means the image distance negative, right? The negative sign in the image distance simply means the image is virtual. The final image, right? Image is virtual. That's the meaning of negative sign in the image distance. Now ray diagram. Let's draw the ray diagram. So this is a convex mirror or diverging mirror. Shape will be like this, right? And this is the principal axis, and you place an object somewhere here. So its focal length is 10. Let's say this is the focal point, right? Symmetrically, and you place an object as 14 centimeter in front of it. So 14. If this is 10, try to be scale. So somewhere here. And again, you're gonna need two rays, right? Two special rays. One is P ray, one is M ray. So now P ray will go like, but this is now diverging mirror, right? It will diverge instead of converging. It diverges, but it diverges, right? How does it diverge? It diverges as if uh, it diver it as if it virtually diverges from this point. So this must be the focal point, right? This must be the focal point. So it diverges as if it diverges from a virtual focus behind the mirror, right? So that's your P ray divergence, right? To P ray reflection. Well, what you're gonna need is now you're gonna need a M ray, right? You're gonna need a M ray, and M ray is this, and that will reflect, right? That will reflect, making same angle of incidence here, right? But now you have to produce them backward like this, and as if it diverges from that point, and they will intersect at a point here, and this is the final position of the image. This is the final position of the, and you can clearly see, since the image is behind the mirror, right? It's virtual and it's upright and it's diminished in size. So our conclusion is the nature of this image is image is first of all virtual because it's behind the mirror, right? Upright and smaller in size, actually diminished in size compared to the object. So that's the case actually. A virtual, I mean, a diverging mirror, which is a convex mirror, right? It always forms a diminished, upright, and virtual image actually, as long as the object is real. Okay, and that's why this convex mirror are used as a security mirror, because it increases the field of vision. So here's the next question. If a man's face is 30 centimeter in front of a concave shaving mirror, right, creating an upright image 1.5 times as large as the object, what is the mirror's focal length? And sketch the ray diagram. So a concave mirror, which is a converging mirror, can be used as a shaving mirror as well. But the object has to be between the focal length and the mirror actually. So that's the problem is, and it will magnify it, and that's why it can be used as a shaving mirror. So it says the object distance is 30 centimeter, right? And so the magnification upright image with magnification 1.5. So upright means the image is upright, right? So positive sign for upright image, and its magnification is 1.5, right? And based on this information, it's asking what is the focal length, right? So magnification is negative di over do, right? So then you can first find this, right? So 30 times magnification is 5, then di is negative 45 centimeter, right? And then focal length will be what? 1 over di, do plus 1 over di inverse, right? And then you can do this calculation. So this is 30 centimeter, but minus, because the image distance is negative. That means virtual image will be formed. The image distance negative simply means it will form a virtual image. That's why it is upright. So that's the focal length. So it's going to give you plus 90 centimeters. So plus simply means it's a concave mirror. That means it's a converging mirror, right? So the focal length of this mirror is 90 centimeter, right? And then uh, sketch the ray diagram. So ray diagram will be something like that. So this is the concave mirror, right? And So this focal length is 90 centimeter, really long actually. So let's say this is 90, right? Let's say symmetrical, right? And you place an object at 30 centimeter, right? So this is, if this is 90, just approximately scaled, right? Something like that. It doesn't need to be exactly scaled, but if you use ruler and everything, it will be accurate. Okay, this is the object, and it's placed within the focal point, right? Focal length and the focus and the mirror, because 30 centimeter. Okay, now how do we do that? So this will now do this, right? And it will converse, right? It has to reflect, because this is a P ray, it has to reflect through the focal point, like this, right? That's the one ray, P ray, right? P ray reflection. Now next is M ray, like this, right? And this will reflect, making same angle of incidence, right? This is the M ray reflection. And obviously now the image will be virtual, because the reflected rays are diverging, right? And diverging rays make virtual image. And how do you find the position of the virtual image? So like always, you have to produce them backward, right? Like this. You need to produce them, this virtual rays backward with dotted lines. And here's the position of the image. So magnified upright image will be found. That's why you can use it as a saving mirror. So if you want to use it as a saving, converging mirror as a saving mirror, you need a really long focal length mirror, so that your face is within focal point and the mirror. And this is the final image position, which is upright, right, and magnified. Here's the next question. Which of the following best describes the image formed by the convex mirror, right? Again, a diverging mirror. When the object distance from the mirror is less than the absolute value of the focal length. So that means first we have to check with the ray diagram, right? So this is the convex mirror, diverging mirror, right? And you put an object here, because this diverging convex shape, right? So it's actually, you put an object, right, between, right, less than is a focal length. That means if this is the focal point, let's say focal point, right, you put an object somewhere here between the focal point and the mirror. Let's say you put an object here. Now let's check with the ray diagram again. So you need P ray, and P ray will, this is a diverging mirror, right? So the P ray will diverge out of the focus, right, as if it diverges from this focus. So you have to draw like this, but this is the real one. So it will diverge, right, from the mirror as if it comes from the virtual focus bay in the mirror. And that's the P ray reflection. Now next you're going to need is the M ray, which again makes the same angle of incidence, M ray reflection, right? And obviously these two rays, right, are diverging, so again they must make a virtual image. And how do you find the virtual image? So you need to then produce them backward like this, right? And they will, in these virtual rays will intersect at the point, and this is the position of the final virtual image. This is the image, this is the object. And if you see, suppose you are the observer, right? If you putting an object, if you see in front of the mirror, you will see a smaller size upright image. So which one is correct? So our conclusion is that the nature of the image is virtual, smaller in size, and upright, right? So that means C is the right answer. These are some problems on lens combination. So we like to find the final image position, you know, due to the combination of lens. So here's the first example, which this principle is utilized in microscope actually. And so it says you have two converging lenses, right? One is, let's say, one is objective, its focal length is 8 millimeter. The second one is eyepiece, its focal length is 60 millimeter, and A microorganism of 10 micron size is placed 8.4 millimeter from the compound microscope whose objective lens has a 8 millimeter focal length. So it's placed actually 8 point just beyond the focal point of the first lens, and it's asking what's the final position of the image and the overall magnification. So the main idea about lens combination is, so the image formed by the first lens works as the object for the second lens. That's the main idea. But if the image formed by the first lens lies in front of the second lens, it works as a real object for the second lens. However, the image formed by the first lens lies behind the second lens, then it works as a virtual object for the second lens. That's the key idea. So let's find that out first. So first, we need to figure out the image position, right? Image formed by the first lens. So we're gonna separately solve that. So for the first lens, which is the objective lens, it says so the object distance is 8.4 millimeter, right? And its focal length is 8 millimeter, right? And it's positive because it's converging lens. So what's the image position? So image position from our formula, you know, 1 over f or minus 1 over d o, right? From the lens formula, thin lens formula. So then you can find that out. So f1 is 8 millimeter minus 1 over 8.4. So di would be 168 millimeter. Okay, so what does it mean actually? The image position, right? The image distance or the image position of the image formed by the first lens lies 168 millimeter from the first lens. So these two lenses are separated by 220 millimeters. So it's somewhere here. So it's so drawing all the figures in scale is a little difficult. So it may not be scale. So the image formed by the first lens, which is real and inverted, right? This is it forms a real image. So it must be somewhere here. Let's say. Right. This is the image formed by the first uh, lens, which lies somewhere here. And look at this focal length. So its focal length is 60 millimeter. And let's see the calculation. So because we just found this as 168 millimeter, right? So and this image works as a real object for the second lens. So then what would be the image distance? So 220 minus 168, right? That's going to be 52 millimeter. So that simply means the image formed by the first lens lies within the focal point of the second lens, right? It lies between the focal point and the second lens. So then the second lens obviously produces a virtual image because its focal point is somewhere here. It's not up to scale, but and then you can do the same thing, right? If you want to draw the ray diagram, you can do that, right? So because it simply works as a real object for the second one, right? And then you do the same thing, right? And so any light ray, so there goes diverging, right? It goes diverging. So that's why it forms a virtual magnified and virtual image somewhere. So it's not up to scale, right? So the final image will be really large, right? Like this, and virtual, right? And this is the eyepiece. So here's the observer, right? We'll see a very magnified, large, right, image. And let's find the final position. So for second lens, which is the eyepiece, right? The object distance is 52 millimeter, and it works as a real object, right? Works as a real object for the eyepiece. So it's positive because it's in front of the lens. So then its focal length is 60 millimeter, right? Given. So then very final image position is again given by this lens formula. So 1 over 60 minus 1 over 52 inverse. But this now turns out negative 390 millimeter if you do this guy. So negative simply means the final image will be virtual image. The final image will be virtual image. Okay, as shown here. So what will be the overall magnification? So overall magnification, right? Total magnification will be m1 times m2, right? So what would be m1? M1 is negative di over do, negative. So 168 divided by do is 8.4, right? And that's going to be 20. And what is m2? M2 is going to be negative di over do. Negative di is negative of negative 390, right? This is actually negative, actually. This came out negative. No, I'm sorry. Yeah. So this is negative 20. M1 is negative 20, inverted. Negative of negative divided by do is 52. So M2 is positive, actually. Positive 7.5, right? With respect to the object. This object is same. So overall magnification is negative 20 times positive 7.5. So it's going to be negative 150. So overall magnification negative simply means it's inverted. Overall magnification will be inverted. Okay. So here's the next question on same lens combination. So it says you have two lenses, converging lenses, right, separated by 8 centimeter distance, and an object is placed 15 centimeter distance in front of a first lens, and lens is focal length is 10 centimeter, its focal length is 12 centimeters, and it's asking what's the final position of the image, right, and overall magnification. Okay, so first do the same thing. Again, the main idea is the image formed by the first lens works as an object for the second lens, right? And again, second important point is if the image formed by the first lens lies in front of the second lens, then it works as a real object. However, if the image formed by the first lens lies behind the second lens, it works as a virtual object for the second lens. That's the main idea. So first let's find the position of the image formed by the first lens. So first lens image position, right? So is do, right? Object distance is 15 centimeter given. Focal length is plus 10 centimeter because it's converging lens. So di is the image position. Image formed by the first lens is now 1 over f1 minus 1 over do, right? Inverse. So then find that out. So it's going to be 1 over 10 minus 1 over 15, and this is plus 30 centimeter, right? So it formed a real and inverted image. Okay, real and inverted image, right? At 30 centimeter distance. 30 centimeter distance is somewhere here, right? So it forms a real and inverted image at 30 centimeter distance, right? So that's simply, now you can clearly see the image formed by the first lens lies behind the second lens. So that means it works as a virtual image for the second lens, because this image would never form actually because of the second lens. It simply serves as a virtual object for the second one. So what would be the final? So since it works as a virtual object, what would be the position actually of this virtual object, which we're going to need for the second lens? So this is 30 minus 8, right? So this is going to be 22 centimeter, but negative, okay, because it works as a virtual object. So for the second lens, what's the object distance? So the object distance do is negative 22 centimeter. Why negative? Because it works as, since it is behind the lens, works as a virtual object, right, for the second one. And its focal length is positive 12 centimeter. So then di is 1 over f2 minus 1 over do inverse, right? And 1 over 12 minus plus 1 over 22 negative 1 di, and di, the final image is real actually, because the image distance is real, right? The image distance is positive. That simply means the final image will be real image, right? And so what's the overall magnification? Let's find out. M2 negative di over do, negative di, di is 7.8 divided by 22 negative y. So M2 will be what? So 7.8 divided by 22 is going to be diminished, right? Am I right? 22, yeah, negative 0.35. And what is M1? Is negative di over do, negative 30 divided by 15. So M1 is negative 2. So overall magnification is M1 times M2, just the product, and it's going to be 2 times 0.35. So negative, no, this is positive, because negative, positive. So negative 2 times 0.35, 0.7 negative. So overall magnification is still, image will still be inverted, right? Overall is inverted, and it will be diminished in size now, because it's less than 1, so it's smaller in size. So now let's talk about the ray diagram, because when the image formed by the first lens lies behind the lens, right, second lens, it works as a virtual image. And if it works as a virtual image diagram is a little tricky. So how do you draw the ray diagram? So here's the trick. So first, in the formation of this image, right, there must be a parallel rays, right, P ray going here, and without this lens, it would just come here and form this lens, right? And there are M ray also is involved, right? M ray doesn't bend. So without this lens in place, right, this is the scenario, right? But with this lens actually, right, because of the presence of second lens, now it will converge. This P ray will be converged to its focal point. So focal point is 8 centimeter. So it's not exactly scaled, but you know, so if this is 22 centimeter, if this is 22, yeah, 30 minus, okay. So this is not to scale, but this will be f2, which is 12 centimeter. So this, instead of this, because of second lens, it will converge now like this, right? And there'll be M ray, right, coming. So now we need M ray, which is the middle ray, which goes undeviated like this, right? And it forms the image. So this is the very final image position. Final image position. You can clearly see it's diminished, right? It's smaller in size compared to the object. So this is how you do that. Okay. Here's the next question. So these are all similar problems. So you have two lens combination. One is diverging lens. The another one is converging lens. And you can treat this as a, you know, this is as a spectacle glass lens, you know, to correct the short sightedness eye, and this is, you can consider this as a eyeball lens. There is a converging lens inside our eyeball, and this combination, this you can think as a glass, and it will help you know, focusing all the rays into the retina to see the image clearly. So here's the thing again. First lens, where you have to treat them separately. First lens is so DO is 15 centimeter, and F1 is negative 10 centimeter, right? Negative because it's diverging. For diverging lens, right, the focal length will be negative. Even if it doesn't say, you have to put negative sign. So what is the image position? Image position will be 1 over f1. 1 is 1 over do negative 1. So 1 over negative 10 minus 1 over 15 is going to give you negative 6 centimeter, right? So that simply means it produces a virtual image, right, at 6 centimeter on the same side actually, right? So you can do that Venn diagram, and it will form in the same side, and it will be upright and diminished. You can see actually, because m1 will be negative di over do, right? Negative 6 divided by 15, right? You can find out the magnification if you want. So 6 over 15 and it's 0.4. So negative and negative, it becomes negative, and negative becomes positive 0.6, 0.4. So virtual diminished image will be formed on the same side. And now, but for the second lens, right, this image, since this image actually is still in front of the second lens, so this, even if this is virtual, it works as a real object for the second lens, okay, because it's in front of the second lens. So for the second lens now, so your object distance is what from this measurement, because we just measure this distance, we just found that distance as 6 centimeter, right? So this is 8 centimeter. So then positive 8 plus 6, 14 centimeter, right? And it works as why positive? Because works as a real object for the second lens. And then its focal length f2 is a converging positive, so di would be 1 over f2 minus 1 over do inverse, so 1 over 12 minus 1 over 14. So final image will be formed at this position, and final image will be, since it is positive, final image will be real. And you can find the overall magnification as usual. So here's one more problem on lens combination. So it's a combination of converging and diverging lens. It says these two lenses are separated by 25 centimeter distance, and it has a focal length of 20 centimeter, while the second lens is diverging lens, concave lens, its focal length is 10 centimeter. And an object is placed at 60 centimeter distance from the first lens, left of the first lens, right, 60 centimeter, and it's acting again. What's the final position of the image? Where the final image will be found? So again, you have to treat them separately, right? So for the first lens, DO is positive 60 centimeter. Focal length is positive because it's converging lens. So DI will be 1 over F1 minus 1 over DO inverse. 1 over 20 minus 1 over 60 inverse, right? And then so it will be 30 centimeter. So 30 centimeter, right? And that's from here is 60, right? 30 centimeter is, and this is 25 centimeter. They are separated by, they may not be exactly scaled. So 25 means it's a real and inverted. So if you check, the magnification is negative di over do, right? So negative 30 divided by 60, right? So magnification will be negative half. So a real and inverted image and diminished image will be formed by the first lens, which will be somewhere here, right? Somewhere here, half the size, right? Now again, this, since the image formed by the first lens lies behind the second lens, right, concave lens, then it works as a virtual object for the second lens. And what's the position of the image object position? So 25. So this whole thing we just found as 30 centimeter, right? 30 minus 25, 5 centimeter, but negative 5 because it works as a virtual object. For the second lens, now do the same thing. Your DO is negative 5 centimeter, right? Because it works as a virtual object. F2 is also negative because it's diverging, right? and your image position is 1 over f2 minus 1 over 5, dO, and 1 over negative 10, negative negative becomes positive 1 over 5, right? So this is going to be positive 10 centimeters. So that means the combination forms the final image as a real image, And what is the final overall magnification? So you need M2 is negative di over dO, negative 10 divided by dO is negative 5. So negative negative positive 2. So overall magnification, right, total is M1 times M2. So negative 0.5 times M2 is 2. So it's same size actually, right? Based on this, it's same size, but inverted. Same size but inverted, right? A real inverted and same size image will be formed. So now let's work on the ray diagram, because if the uh, object, if the uh, image formed by the first lens lies behind the second lens, right, it works as a virtual object, and if it works as a virtual image, the ray diagram is a little tricky. And how you do that is this. Again, you have to, so in forming this, um, in the formation of this image, there are several special rays are involved, right? One is the F ray. This is the F ray, right? This is the F ray that is involved in making, because without, if there's no this diverging lens in this place, actually it will, the F rays, right? F rays means 20, this is the F ray, right, is involved in, because any light rays passing through the focus will go parallel, right, parallel P ray, and it will go this. And the next one is the M ray, and these are the light rays involved, right, in forming this image. If there's no diverging lens in this place, right, these are the rays, right, that is used in forming this image. But because of the diverging lens, right, in this place, so this P ray, right, this now it works as a P ray for the second lens. It now diverges, right, and it's 10 centimeter is somewhere here. Let's say f2, 10 centimeter, right. It will diverge as if it diverges from its focal point, right. It will diverge away like this, right, from f2. Instead of just going like this, it will diverge because of this. And you need a M ray, and that M ray will, because there are a stream of light rays coming, actually striking this lens from after converging from this. So you need a M ray, one M ray who is involved like this, and this is the final position of the image. So this M ray, this is the divergent ray coming, which is coming from this F ray from the first lens. And this is how you draw the ray diagram if the object is virtual. So this is the very final position of the image, and you can clearly see the final image is formed by actual convergence of the beam, right, light ray. So its final image is real image, real and inverted and same size image which we have calculated.